During our study of electricity and magnetism, we've developed some very critical relationships, and we watched them sort of accumulate on the window of the classroom. We know that we're heading somewhere that's very meaningful. Two laws that we've already used to great utility appear here, laws of electricity. The first, obviously, is Gauss's law, where the integral of the electric field dotted into the differential of an area, the quantity that we refer to as electric flux, is equal to 1 over epsilon naught the integral of rho dV. The idea here being that the electric flux into or out of a volume of space is proportional to the charge that is enclosed inside of that volume. We leverage this equation to understand the distribution of charges in space, or more commonly, to calculate the electric field. The second equation I've written in a little bit of a strange form. The integral of E dot ds we typically write as being equal to the negative of the potential difference in space. But notice here in this version that I've written, I have a halo written on the integral. That means the path along which this integral is performed is a closed path. It starts and begins at the same location in space. As you might expect, a particular location in space has a very specific electric potential. So if I integrate around any closed path, that integral should be equal to the change, should be equal to the negative of the change of the electric potential along that path. Starting and finishing at the same point in space, that electric potential difference should be equal to 0. Now, this law is written in the context of the electric field in general, any arbitrary path through space. But we've also used this when working on circuits. When I select a point in an electric circuit, and I go around observing the potential differences along the resistors and capacitors and batteries that I encounter along the way, I find that if I close that loop and finish that investigation at the same point in the loop that I started, then the net potential difference around any closed loop of an electrical circuit is equal to 0. This law is an expression of just that. So far, we've found more use, greater utility, from the version of this equation that does not have the halo. Here, I've added the halo because it gives me some interest going forward. These are the magnetic field equations that we've arrived at through the course of our study. And first I see the integral of B dot dA, something I might refer to as magnetic flux, again with the halo on it, but unlike Gauss's law, where I have the right-hand side being so interesting related to the charge enclosed by my Gaussian surface, here it's equal to 0 because there are no magnetic particles that are the source of magnetic field. There's no point objects that create or the source of magnetic field, and similarly no sink of magnetic field, because as I know, the magnetic field lines form closed loops. And so that seems to be a really obvious conclusion, but it turns out I'm gonna find that equation still to be useful. The next equation, of course, is Amperes Law, that the integral of the magnetic field around a contour, the complete integral around the contour, is equal to the permeability of free space times the integral of J dot dA, where J is the current density, and that integral represents the current that flows through the closed loop. And I recall, much like Gauss's law, that current that is outside of the loop does not contribute to the integral, and current that is inside the loop contributes. And I can use Amperes law very much the same way that I would use Gauss's law for finding magnetic fields in some region of space, particularly where there's some symmetry that I can take advantage of. And the number one application of that is finding the magnetic field due to an infinitely long wire. So here I have two sets of equations that I've devised so far. I have a set of electricity equations, electric field equations, and I have a set of magnetic field equations, and they are not related one to the other. There seems to be no connection between the two. It turns out to be the case that at the end of the 1800s, just from a historical point of view, that electricity and magnetism were believed to be two separate physical phenomena. They didn't even scale the same. The permeability and the permittivity scale factors don't seem to have a clear relationship. So what we need is another experimental observation that demonstrates to us that the electric and magnetic fields are actually in some way related. It took a little bit of time for that to happen because the effect is quite small. There is a very important demonstration that we should do to observe this effect. I can't do the demonstration live, but I can do the demonstration in the context of a computer simulation. Here I have the now familiar representation of a bar magnet in space. And in this region of space, I have a very, very large number of compass needles that are indicating not only the direction of the magnetic field at that particular point in space, but also sort of relative magnitude. Notice as I go to the outer edges of the field here that the needles fade out. The brightness of the needle is intended to give me an idea of the intensity. So I see that the needles that are closest to the magnet are lit up very brightly and that they fade the further I go from the magnet. The magnetic field lines that I can almost imagine here, I see are exactly what I expect. They form closed loops. Now, at the moment, I can't see the magnetic field inside of the magnet, but here I can represent those now. The magnetic field lines inside the magnet go from the North Pole to the South Pole and are very strongly aligned inside of the magnet. I would see here, if I was drawing a great many field lines, a large number of magnetic field lines very close together inside of the magnet, forming closed loops with the compass needles outside in this region of space. So if I take this magnet, my interest in showing this to you is if I take this magnet here and I move around in space, all of the compass needles everywhere in space react, not instantaneously as it happens, they react at the speed of light. But they all interact and change their orientation in space, and they change their brightness according to intensity. And I realize that as I move the magnet around in space, I change the magnetic field, magnitude, and direction everywhere in space. It's not just my fixed magnet that'll do this, but it'll also do if I create a magnetic field using an electromagnet. Here I have a battery connected to a coil of wire. The wire, according to the Biot-Savart law and the application of the right-hand rule, creates magnetic field in its vicinity. Similarly, if I grab this apparatus and I move it around in space, I see magnetic field lines that are very much the same in terms of their geometry and shape in space as the bar magnet. And when I move it around in space, I change the magnetic field everywhere in space. If I increase the voltage, naturally, I increase the current and I increase the magnitude of the magnetic field created. If I set the voltage equal to 0, naturally, I get 0 magnetic field in space. If I make it negative, then I get a magnetic field that points in the opposite direction, or I should say, circulates in the opposite direction. Here's the interesting experiment, and one that I would have demonstrated for you live. Here I have a bar magnet and a coil of wire in the same region of space together. As expected, I see that the bar magnet is creating magnetic field in its vicinity. The loop of wire is not creating any magnetic field at all because it is not attached to a power supply or source of potential difference that would create a current. It is, however, connected to a voltage meter that can measure the potential difference in the loop of wire. You might think at first that this is a bit silly. Without a source of EMF, without a battery, then I don't expect that I would see any voltage at all inside the battery. And indeed, the voltage currently reads 0 volts. If I go over here and grab hold of my magnet and move it around in space, I see what I expect as the magnetic field changes everywhere in space. Indeed, the magnetic field due to this particular magnet seems to be a bit weak. The needles fade out significantly as I go to the edges of the diagram. But nevertheless, moving the magnet around in space changes the magnetic field in space. Even the magnetic field in the vicinity of my wire loop. Now let's watch for the interesting effect. Observe what the voltage meter does as I bring the magnet close to the loop. Observing the voltage, I wait a second, there was a little bit of a hitch there. As I move the magnet around near the loop, I find that almost nothing happens. I say almost is because when I got to the loop, bring it closer and closer and closer, the magnetic field got stronger and stronger and stronger. There was the slightest blip on the voltage meter as a result of the motion of the magnet. Now, here's the reason why we did not realize this relationship between electricity and magnetism previously. The experimental effect that I'm observing here is quite small. If I were doing this live with a bar magnet and my solenoid, I would be using a voltage meter that is extraordinarily sensitive to potential differences, small potential differences. In fact, such a device is known as a galvanometer. It measures voltage not in volts but in galvines, which is a very small scale measurement of voltage. So I get a very, very small effect. I can, curiously enough, make the effect larger by moving the magnet faster. So far, I've been moving the magnet slowly in the vicinity of the loop. Now, I'll move the magnet vigorously on this side of the loop and see that there is no doubt about it. The needle tremors as I move the magnet back and forth in the vicinity of the loop. Watch how dramatic the effect becomes when I move the magnet completely through the loop from left to right. As I move the magnet through the loop, the effect becomes very significant. You might not be surprised by that because as I move the magnet through the loop, the magnetic field in the vicinity of the loop becomes largest in magnitude. But if I just take the magnet and place it in the middle of the loop, you see that the voltage reads 0. If I place the pole of the magnet in the center of the loop and let it rest, the voltage reads 0. There seems to be some kind of association between the motion of the magnet and the voltage that I read on the loop. But of course, the effect is quite small. What I'd like to do is magnify the effect. I can do that by increasing the number of loops that I have. Here, I increase the number of loops from just 1 loop to 2, and from 2 loops to 3. It'll turn out in the final analysis that the amount of effect that I get is multiplied by the number of loops that I have. Now, when I move the magnet in the vicinity of the loop, I get a more dramatic effect. And in fact, I get a significantly larger effect as I pass the magnet through. Here's something that I noticed that's curious. I get 1 voltage as I move toward the loop. Do you see, as I move the magnet towards the loop, it seems to be deflecting in the negative direction. It's challenging to see. You have to wait for me to move it. 3, 2, 1, go, and realize that the needle deflects to the negative direction when I do that. If I take the magnet and I move it away, I see that the needle deflects to the positive direction. So it seems that this effect that I'm observing, the presence of voltage in my coils, depends not only on the motion of the magnet itself, but also the direction of motion of the magnet. Of course, this is some sort of interaction between the magnetic field and the coils of wire, but indeed it's very, very mysterious. It's going to take some careful thinking in order to take this actual phenomenon and devise from it a physical law. In constructing my physical law to describe this effect, I find that the notion of magnetic flux becomes useful. Here I've written it again as phi sub m, implying the magnetic flux is equal to the integral of b dot dA. Now you might immediately jump the gun and say, hang on a second, we decided that that was equal to 0 because there are no magnetic monopoles. Look closely and realize I haven't put a halo on the integral. What I'm describing here is not the flux through an enclosed surface by the magnetic field, which of course would be equal to 0, but instead the flux through a loop, like the coil of wire in my experiment. This magnetic flux is defined exactly the way as my electric flux formerly when I studied Gauss's law. I look for the component of the magnetic field that is perpendicular to the loop, that is, the component of the magnetic field that actually goes through the loop. Components of magnetic field that are parallel to the loop don't flux the loop, and so therefore don't contribute to this integral. Also, any magnetic field that is outside the loop, does not have an effect on calculating the flux integral. The reason why magnetic flux matters here is that as I do the experiment, I realize that as the magnet gets closer to the loop, the effect becomes larger. Well, I could simply say that this was based on the magnetic field strength at that instant in time. But what I would discover is that doesn't account for the geometry of the loop. That is, the loop has some cross-sectional area. And also, I would end up with an incorrect result for my physical law. Instead, I realized that what's going on is that the magnetic field that matters to the effect is the magnetic field that actually penetrates the loop of wire, or loops of wire if I have multiple. And this is the quantity that's of interest to me. But this on its own is not sufficient. If I simply look at a static situation where the magnet's at rest and the loop is somewhere in space in the vicinity of the magnet, certainly I can calculate this integral and I can find out how much magnetic flux there is through the loop. But nothing happens unless the magnet moves. And when the magnet moves in space, the magnetic flux is changing in time. And that, as it happens, is the whole secret to this phenomenon. In the experiment, we observed that a current would flow inside of the rings when the magnetic field in the vicinity of the ring changed in time. That flow of current was caused by an EMF, a potential difference around the loop that shouldn't exist, because around the closed loop, the potential is equal to zero. There are no batteries. And yet it seems like there is an EMF that is simply created by the changing magnetic field in the vicinity of loop. Therefore, much like induced charge that we discussed early in our study of electrostatics, we refer to this as induced EMF. EMF that is created by the changing magnetic field. The final physical law, which we use to describe this effect, is known as Faraday's law. Here, the induced EMF is equal to the negative of the derivative of the magnetic flux with respect to time. Notice that it doesn't just depend on the magnetic flux itself, which is necessary but hardly sufficient. What needs to happen is the magnetic flux needs to be changing in time. The magnetic flux integral that I would calculate in any instant in time needs to be increasing or decreasing in order to create an induced EMF. Now, if the magnetic flux is increasing, then I'm going to get a positive result for this derivative. Faraday's law itself has a negative sign, which means, quite curiously, that if the induced EMF, if the magnetic flux is increasing, the induced EMF will be in such a way as to oppose the change. And that's an idea that we're going to keep in mind throughout the entire discussion, not only in this video, but in the videos to come. The induced EMF in a loop opposes the change in the magnetic flux through that loop, and that's the reason for the negative sign. It'll turn out from a practical point of view that we won't often use that negative sign to determine the algebraic result, because the negative sign here is more of a concept of the oppositional nature of the induced EMF. Instead, what we'll do is we'll use the rate of change of the magnetic flux to calculate the magnitude of the induced EMF, and you would not be at all surprised to learn that we'll use a new version of the right-hand rule to determine the direction of the induced EMF. That is, whether it goes, say, clockwise or counterclockwise from a certain point of view. This induced EMF is what causes charged particles to move through the wire. And so we observe in our experimental apparatus a current caused by that EMF. But ultimately, EMF, we know, is related to the electric field, because it's still true that a potential difference is equal to the negative of the integral of the electric field dotted into the displacement. That's still true. And so when I say that there's an EMF around a closed loop, that immediately implies that there is electric field in the vicinity of that closed loop. And that's a rather remarkable statement, because here we have, for the first time, magnetism being directly associated with the electrical effect. So I want to flesh it out here a little bit and see the relationship between the electric and the magnetic field expressed in a single law. So here I have my induced EMF according to Faraday's law, which is the negative of the derivative of the magnetic flux with respect to time. I just realized I wrote a phi sub b there instead of a phi sub m. It's actually my style to write phi sub b, but that's what I mean, the magnetic flux. There's no difference from earlier on in the discussion. But the magnetic flux, phi sub b here, is the integral of b dot dA. So I end up writing that the induced EMF, E sub L, is the negative of the derivative with respect to time of the integral of the magnetic field dotted into the differential of area. Look at that! And very often at this point in time, AP Physics students see that equation and they say, can you do that? Can you take the derivative of an integral? Well, of course you can. First of all, the integral, well, a thought that you might have is, if you take the integral and then you take the derivative, you just get the same thing back again. That's not what's going on, because the integral is the integral of the magnetic field with respect to the area, and the derivative is a derivative with respect to time. Now, in order for this thing to result in anything other than zero, my magnetic flux, the integral of b dot dA, has to work out to be time dependent. There are three different ways that that can happen, but let's just imagine that b dot dA has some time dependence to it. Integrating with respect to area has no effect on time dependence whatsoever. In a sense, when the integral is being performed, time dependence is constant. After the integral is performed, the result of the integral is time dependent, and so then I can take that derivative. You might be anxious at the moment to see how that works out in the demonstration of problems, but that's going to have to wait until the next lecture. So that's what I have on the right-hand side of this law, essentially Faraday's law of induction. On the left-hand side, I have the induced EMF, which, as I've already explained, is related to the electric field. Here's explicitly how. The EMF, E sub L, is induced around a closed loop and is in fact equal to the integral around a closed loop of E dot ds. Formerly, we had said that that integral must be equal to zero. Now we realize, after an experimental observation, that that integral around a closed loop of E dot ds is not in fact equal to zero, but is equal to the negative of the derivative with respect to time of the integral of the magnetic field dotted the differential of area, a magnetic effect, which is very, very small. If the magnetic field is not present, then I would not, obviously would not observe this effect at all. And when the magnetic field is present and the flux is changing with respect to time, the effect is small. So this is sort of historically the next thing that we discover. The reason why, the very important reason why I show this diagram here, is because I wanted to show how I have electric field on the left-hand side of the equation, and I have magnetic field on the right-hand side of the equation, which shows the relationship between electricity and magnetism. Sure, the relationship between the two is complicated, but nevertheless, there's a relationship between the two, and ultimately the discovery that is made here is that electricity and magnetism are not separate phenomena, but they are in fact two different aspects of the same phenomena, electromagnetism. Here I'm showing a region in space where I have a magnetic field directed into the screen. You can tell by these X's, as I've distributed throughout space, evenly, which means the magnetic field is uniform. It's the simplest possible situation that I should describe. So this magnetic field, uniform everywhere in space, and we've already talked about such fields in terms of how they deflect the motions of charged particles and so on. But what I'm going to do here is have this magnetic field directed into the screen and increase the magnetic field. I don't particularly care how it's done. There must be some source of magnetic field around somewhere which is being manipulated. Perhaps this is the magnetic field inside of a solenoid, and I'm simply increasing the current inside the solenoid, which would increase that magnetic field. However it's done, here I have magnetic field directed into the screen, and that magnetic field is increasing. Therefore, if I choose a sort of Amperian loop in the plane of the screen, in particular, if I choose a circular Amperian loop, what I would discover is that some of this magnetic field fluxes that loop. And since the magnitude of the magnetic field is changing, that means that flux is changing in time. The changing flux in time induces EMF. But more fundamentally, it induces electric field. Now the relationship, of course, is that the integral around a closed path of the electric field dotted into the differential displacement is equal to the negative of the derivative with respect to time of the integral of the magnetic field dotted in the differential of area. But let's see what we get on the left-hand side. If I choose the origin of my coordinate system to be at the center of the thing, then performing the integral on the left-hand side is rather simple, because the integral of E dot ds becomes the integral of E times ds, becomes E times the integral of ds, becomes E times 2 pi r. Induced electric fields form closed loops. And so here I've shown these concentric circles, which are lines of electric field which circulate. And you think, wait a second, hang on. This means that there are electric field lines that are created in space without there being source charges. Where is the positive charge that is the source of this electric field? Where is the negative charge that is the sink of this electric field? Well, fun thing that we discover here. This electric field is induced without the presence of charges, which means the electric field exists independent of charges, which you already know because at the end of our discussion of capacitors, I had realized, made the realization, used the capacitor energy to demonstrate that electric field itself has energy associated with it. There is electric field energy. That energy per unit volume, by the way, was 1/2 epsilon naught the electric field magnitude squared, which implied that if there's energy associated with electric field, the electric field exists when there are no charges. And here, I have no electric charges anywhere, and yet electric field is induced and created in region space. I could use the equation at the bottom of the screen in order to calculate what that electric field is. That is, I could calculate its magnitude, just as I suggested, the left-hand side working out to be the electric field times 2 pi r, and the right-hand side working out to be whatever that flux was through a circular area, and calculate how much electric field that I would expect as the magnetic field changes in time and the flux changes. And so I could calculate that. Well, obviously, yes, we'll need some practice doing that, and we'll need to see some demonstration of that procedure taking place, but we realize that it can be calculated. The strange thing is, though, here I've drawn the electric field in this situation, circulating counterclockwise along the circular loops that I've drawn here. How do I know that? How do I know that the electric field is induced in that direction and not in the other direction? Well, the answer, of course, is a right-hand rule. And so now it's time to discuss that right-hand rule. We already have 2 right-hand rules in our toolbox of things that we can use to solve these problems. The first is the rule for finding the force of magnetism. If I have a particle moving with a velocity v through a region of space that has a magnetic field, then I point my fingers in the direction of the velocity. And I curl my fingers in the direction of the magnetic field. My thumb points in the direction of the result of the cross product. If it's a positive charge, then that's the direction of the force. If it's a negative charge, then the force is opposite that. We've had some practice applying that right-hand rule. I also have a right-hand rule for the field created by a wire. I point my thumb in the direction of the current, and my fingers, that is, in the direction of the conventional current, that is the flow of positive charges. I point my thumb in the direction of the conventional current, and my fingers curl in the direction of the magnetic field. Well, now, we have a third right-hand rule. This particular right-hand rule is the most challenging of the 3, so at this point, some very, very careful thinking. And probably, you're not going to get this on the first go. There'll probably be some more discussion of it. What I need to do to determine the direction of the induced EMF, or indeed here the direction of the electric field, is to point my thumb in the direction of the magnetic flux. Now that's a weird thing to say, because magnetic flux is not a vector. The magnetic flux is the integral of B dot dA, which is a scalar product. Magnetic flux is not a vector, so what I really mean is to take the thumb of your right hand and point it in the direction of the magnetic field, which in this case is into the screen. Now, I made the declaration at the beginning of the problem that the magnetic field was increasing, which means the flux into the screen is increasing. Notice that my law has a negative sign in it. This is where the negative sign comes in. I have my thumb pointing in the direction of the field, and the field is increasing, which means the flux is increasing, and I want to oppose the change in flux. I want to invoke that conceptual negative sign by reversing the direction of my thumb. My fingers then curl in the direction of the induced EMF. My fingers curl in the direction of the induced electric field. I'll summarize again. I point the thumb of my right hand in the direction of the magnetic field. I declared in the problem that that magnetic field was increasing, so the flux in that direction into the screen is increasing. To oppose it, I reverse the direction of my thumb, and my fingers curl in the direction of the induced electric field. In this diagram that I've drawn here, I have magnetic field and I have electric field, but I don't have any loops of wires. When I did the experiment, I had a physical bar magnet in my hand, and I had a physical loop of wire, conductor, probably copper, that I had fashioned, and I moved them near each other and I saw the effect. The effect doesn't have anything to do with the magnet, the physical magnet. It doesn't have anything to do with the actual conducting wire loop. It is a relationship among the fields themselves. Now look at this region of space where I have some magnetic field and some induced electric field. There's no wire loop. There's no current. There's no voltage here. Well, I mean, because I have electric field lines, you could calculate a potential difference between field lines, and there would be voltage associated with that. But nothing's happening in this diagram. But imagine if this effect was taking place in space and you fashioned a loop of wire and held it up in this region of space. Perhaps you made it, the wire into a circle that was the same diameter as one of the circles that you see in the diagram, and you held it up right there. That electric field that you see in the diagram would cause the charged particles inside of the wire to begin to move. And so you would see current. And with that current observed and the resistance of the loop, you would say, well, that's voltage. That's induced EMF. An induced EMF appears in a physical wire loop as a direct consequence of the induction of electric field in the region of space where the loop happens to be. So I have a law of electromagnetic induction given to me by Faraday, and what I'd like to do is imagine how this will manifest itself in practical situations that I might encounter, some basic fundamental examples that I can investigate that'll then ultimately translate into engineering applications of this principle and this observation that I've made. So here I have electromagnetic induction, which means I get an EMF that is induced in a wire loop as a result of a magnetic flux that has some time dependence associated with it. If the magnetic flux is in any way, well, there's only one way, for it to be constant in time, then the derivative of the magnetic flux with respect to time is equal to zero, and there'll be no induced EMF whatsoever. So I'd like to break it out and discover what are the ways in which I can have a time-dependent magnetic flux. The magnetic flux is equal to the integral of the magnetic field dotted into the differential of area. So what I need is for that integral itself to be time-dependent. Well, the integral contains this dot product, B dot dA, which I know is the magnitude of B times the magnitude of the differential of area multiplied by the cosine of the angle between them. So what I need is one of three things or a combination. I either need time-dependent magnetic field or time-dependent area, or I need the angle between the magnetic field and the area to be time-dependent, or I need some combination of the three. This sets us up really well for the next video, because what I'm going to do is to contrive an example of the application of Faraday's law where the magnetic field is a function of time. This will be easy to do. I'll simply say B equals and some equation for the expression of B that has time dependence. I can think of all kinds of crazy things. I could have polynomial dependence. I could have sine, cosine function dependence. I could have exponential dependence. Just B written as a time-dependent expression. And then I'll do an example of the area as a function of time. It's really easy to think of how I could do that. I did the experiment with a circular wire loop. Imagine that I have control of that, where I can pull on an end of the wire and make the radius of the circular loop smaller, or I could push against it and make the radius of the loop larger, and so therefore the area would be a function of time. The angle of a function of time is the most interesting, and as it turns out, the most technologically relevant. As a matter of fact, the success of the whole human race thus far really relies heavily on the angular time dependence concept. So I have a magnetic field and I have a loop of area. So what I could do is I could turn the loop in space. And since the area vector is perpendicular to the loop, then the orientation of the area vector with respect to the magnetic field vector would change in time. And that would be the angle theta having time dependence. There's another clever example that appears on a lot of AP examinations. And so in the very next video, I'll be solving these three problems.